Let's look at an example that uses these new vocab terms and equations. A 3-kilogram mass is attached to a spring. The mass is pulled 15 centimeters and then released, setting the mass spring system into simple harmonic motion. The system makes 12 oscillations in 9 seconds. Letter A, determine the period, frequency, and angular frequency of the resulting motion. And B, what is the spring constant of the spring? All right, let's start with period for letter A. So I know that period depends on the mass and the spring constant, but the problem is I don't have the spring constant. So I'm going to have to find period a different way. So I'm going to instead use its definition. And it says here that the system makes 12 oscillations in 9 seconds. And I know that period is measured in seconds. So that tells me that I could say 9 seconds is 12 oscillations, and that would give me the time for one oscillation. And the time for one oscillation is 0.75 seconds. When I want to find the frequency, it's the inverse of that. It's how many oscillations occur in a second. So 12 oscillations over 9 seconds gives me a frequency of 1.33 1 over seconds, and a 1 over seconds is called a hertz. I could also have calculated the frequency knowing that it's the inverse of period, so 1 over 0.75 also would give me 1.33 hertz. Angular frequency means that I'm going to take my frequency and I'm going to multiply it by 2 pi so that I turn it into radians per second. And because a radian per second, because a radian is not a true unit, it turns out to be 1 over seconds, which means a radian per second is also equal to a hertz. So 8.38 hertz. So now in part B, I'm supposed to find the spring constant. So now this might be a good time that I could use the period equation. Period equals 2 pi square root of m over k, because I know the mass and I'm solving for k and I know the period here. When I'm solving for something under the square root sign, I find it easier to square everything, so that's what I did. I squared the 0.75 period, I squared the 2, that gave me the 4, I squared the pi, gave me a pi squared, and then 3 over k, and then I just solved for k. And I have a k value spring constant of 134.04 newtons per meter. Part C says, sketch a displacement versus time graph of this motion. Show at least 2 periods of oscillation and label key values on the x and the y axes. So I actually have the answer to the question already drawn here, but let's talk about how you would know what to draw and how do you know where to start. So the first thing that should go through your mind is if I have to draw a displacement time graph of something that's in simple harmonic motion, the graph is going to be sinusoidal. So I know it's going to look like a sine wave or a cosine wave or a shifted sine wave. The next thing is you need to know about the start of the story. Like, how do I know where to start my wave? So it says the mass is pulled 15 centimeters and then released. So that tells me if this is equilibrium, that this mass spring system was stretched. Now I know where to start my wave. So I also know the key values on the y-axis, because now how far did I stretch it? 0.15 meters. And I made that negative. And now you can just draw some random cosine. This is actually a negative cosine wave. Just draw the wave. And I know that it goes down negative 0.5, and I know that it's going to go up to positive 0.15. So I'll make sure that those look symmetrical. Now I have to scale the x-axis. I know that the x-axis stands for time. So what is a key value of time that I would know? I know the period of motion. The period is the time for one complete oscillation. And one complete oscillation is 4 amplitudes. So that's 1, 2, 3, 4. And so the time on the x-axis here, I could scale this, would be 0.75 seconds. That was the period for one oscillation. And I'm supposed to show 2 periods. So I'm going to draw another one. 2 t would be 1.5. And really what I've done now is I've given myself enough values that I could scale the x-axis if I wanted to. But that's what they're talking about when they say label key values on the x and y-axis. We want the amplitudes on the y-axis and we want the periods or time measures on the x-axis. Letter D says write the position function for this oscillating system. So if I have to write a position function, I'm supposed to know these forms. I copied them up here so that we could look at them. And it's also helpful to have the graph handy. So I have the graph from letter C that I copied here also. So when I write the position function, I know it's going to be either the sine version or the cosine version. And I look at my graph and I remember that it was stretched. So that tells me that I'm at an end point. So it's going to be the cosine version. So I'm just going to write down the cosine version. So what I have to do now is I have to replace the variables that I know. So I'm solving for x. So I'm not going to replace the x, but I do need to replace the a. And I do need to replace the omega. I'm going to leave t alone because t is going to be the variable that makes it the position function. All right, so the amplitude at the start of the story, the amplitude is negative 0.15. And we also calculated omega back in letter A was 8.38. This now is called the position function. I have these values in here, but I kept the variable t because now when I want to use the position function, I can plug in any value of t that I want, and I can solve for the x, the location of the mass on the y-axis. So letter E says, calculate the position of the mass at a time of 0.7 seconds. So let's look at our graph. This is 0.75 seconds. So 0.7 seconds, the mass is down here, someplace down here. But I don't really know exactly where, but that's where the position function can help me. So now we're going to actually use our position function to make that calculation. So now I'm going to plug in for t, I'm going to plug in the time 0.7 seconds, and now I just have to number crunch and solve for x. But remember, when you use the position function, your calculator has to be in radians because this 8.38 is in radians and you're taking cosine of something in radians. I did this in small steps so that we can check your calculator work along the way. So 8.38 times 0.7 is my 5.87. Now I'm going to take the cosine of that. Remember, my calculator's in radians, and I get 0.914. If you get the 0.914, you know you're doing it correctly, and if you don't, your calculator's not in radians. Times negative 0.15, and I get an x value of negative 0.14. That tells me where the mass is on the y-axis. This is the displacement on the y-axis. So on the y-axis over here, I am at negative 0.14 meters, and negative 0.15 is the maximum, so I'm pretty close to the maximum. So does this make sense according to our graph? Yeah, it does. So that's one good thing about using the position function is you can kind of check your answer by looking at your graph as well. And letter F says calculate the maximum restoring force. The maximum restoring force can be calculated from Hooke's law, F equals kx. The spring constant is 134.04 times the maximum displacement gives me a maximum restoring force of 20.12 newtons. And then finally letter G, what is the maximum acceleration of the mass? I'm going to get this from F equals ma. And the net force is the restoring force equals ma. So the restoring force, which is kx, we now know is 20.12. The mass is 3 kilograms. So the maximum acceleration is 6.7 meters per second squared. And letter H says, sketch an acceleration time graph of the motion. Show at least 2 periods of oscillation and label key points. So we just calculated the maximum acceleration and it was 6.7 meters per second squared. So the answer to this question is already shown right here, but let's talk through how you would get this graph. I find it easiest to get the acceleration time graph when I'm looking at the displacement time graph. So I copied the displacement time graph here. We remind ourselves that we set the system into oscillation by pulling the mass down a displacement. This displacement is a negative value. And from Hooke's law, that tells me that the acceleration has to be positive. So now I know that it is a positive 6.7 meters per second squared, where this graph has to start. And the rest of the graph, since we didn't change the mass or the spring constant of the spring, that means the period is not going to be changed. So the 0.75 and the 1.5 is going to be the same. And we also remember that the acceleration time graph is the same as the displacement time graph. It's just flipped upside down, 180 degrees upside down. So we can get this exact same graph looking like this. You should also be able to extract information from a graph. So here's a second example problem that involves a graph. How about this time you stop the video and see how many of these questions you can answer yourself, and then hit play when you're ready to check your answer. All right, letter A, what is the amplitude of motion? I can read the amplitude right off the graph, 0.6 meters. Letter B, how long does it take for one complete oscillation? I can see that that is 2 seconds. Letter C, determine the frequency of motion. Frequency is 1 over period, so 1 over 2 is 0.5 hertz. Letter D, what is the angular frequency? That is taking my frequency and multiplying by 2 pi. So I get an angular frequency of 3.14 radians per second, or hertz. Letter E, write the position function of the mass. So the position function is going to be a sine or cosine version. And I can see at the start of the story, my mass is stretched. So that tells me it's going to be cosine. I put a negative in there because I'm starting down in the negative y direction here. So I have to replace that amplitude though with its appropriate value, so negative 0.6. And then I have omega. So I could have just plugged in my 3.14 down here and been done with that. But I just wanted to show you another way that you'll see it happen sometimes. So instead of just plugging in this number, we could say that omega is equal to 2 pi f. And we know that f is 1 over the period, so 1 over 2. And now you can see that the 2's cancel, and I end up with a pi left. The pi is the 3.14. But by leaving it in the pi form, instead of rounding to 3.14, I'm going to end up with a more exact answer for calculating x. All right, the next thing is letter F, calculate the position of the mass at 3.8 seconds. So let's do a little predicting first. So 3.8 seconds, there's 3.5, 3.8. So I think it's going to be something negative down this way, something this way. So I'm just going to use my position function now that I just wrote. And I'm going to plug in the time of 3.8 times pi, take the cosine of that, times negative 0.6. And I get negative 0.49 meters. And so negative 0.49 meters. So yeah, that kind of makes sense. I can see that right there on my graph. And then letter G, calculate the spring constant of the spring. And we could use our period equation to do that. And again, we're solving for K. And I didn't show my algebra due to lack of space, but I ended up with a K value of 29.61 Newton meters.